The birth of a central processing unit, or CPU, is a journey of precision and complexity that rivals the finest works of art. When we think of masterpieces, we often think of paintings, sculptures, or even symphonies. But what about a central processing unit? To many, it's just a piece of hardware, but in reality, it's a marvel of modern engineering and a testament to the power of human ingenuity. CPUs are the brains of any computer. Whether it's a smartphone, a laptop, or a supercomputer, these tiny chips are responsible for executing the instructions that allow us to browse the internet, edit photos, run simulations, and so much more. They are the heartbeat of our digital lives, and without them, the world as we know it would come to a standstill. But where does this journey begin? It starts with something quite ordinary: silicon. The second most abundant element on Earth, silicon forms the backbone of every CPU. But don't let its abundance fool you. The process of turning this common element into a CPU is anything but ordinary. It requires a level of precision that is almost unimaginable, akin to crafting a sculpture on a single grain of sand. This journey of precision begins with drawing large, perfect silicon crystals from purified silicon melts. It's a delicate process that demands a dust-free environment to avoid contamination from impurities. Imagine a room so clean that a single speck of dust could potentially compromise the entire operation. That's the level of cleanliness required in these clean rooms. Once the silicon substrates are ready, they move on to the next stage: photolithography. This involves using light and a photosensitive resist to transfer circuit structures to the wafers in a template-like fashion. The tiny transistors themselves are generated from the unprotected areas of the wafer surfaces, paving the way for the next step: ion implantation. The journey begins with a humble piece of silicon, but by the end it will be transformed into the brain of a computer. The art of precision manifests itself every step of the way, from the first crystal drawn to the last ion implanted. This is the story of how a CPU is made. The transformation of silicon into a CPU begins with the creation of a silicon substrate. Let's go on a journey to discover how this process unfolds. Silicon is not just any ordinary element, it's the second most abundant element on Earth. And it's the magic ingredient in our technological world. But before it can power our devices, it undergoes an extraordinary metamorphosis. The first stage in this transformation involves drawing large, perfect silicon crystals from purified silicon melts. Picture a vat of molten liquid silicon. It's heated to over 1400 degrees Celsius, turning it into a fiery liquid state. A small seed crystal is then carefully introduced into this molten silicon. As the seed crystal is slowly withdrawn, the silicon solidifies around it, forming a single, giant crystal. This is not a process that can be rushed. Perfection takes time. Yet, even in this process, danger lurks. Any impurities can compromise the manufacture of these substrates. A single speck of dust, a lone particle, can render an entire silicon wafer useless. This is why the entire process takes place in dust-free clean rooms. These rooms are meticulously maintained to ensure that no unwanted particle intrudes. Think of it as a surgical operation where the smallest of impurities could have catastrophic consequences. After the crystal is grown, it is sliced into thin wafers. These wafers will serve as the base or substrate upon which the intricate circuits of a CPU will be built. Each wafer, a potential powerhouse of processing capability, is a testament to the marvels of modern technology. The journey from silicon to substrate is a delicate dance, a ballet of precision and purity. It's a process that requires both meticulous attention to detail and an immaculate environment. The creation of silicon substrates is a delicate process requiring both precision and an immaculate environment. With the substrate ready, we're one step closer to the heart of our digital world, the CPU. The silicon's journey continues, and so does ours. Let's move forward, shall we? With the silicon substrates ready, the next step is to transfer the circuit structures onto the wafers. Enter the fascinating world of photolithography, a process that blends science and art in the creation of intricate microchip designs. So, what's photolithography? Well, it's a method that uses light and a photosensitive resist to imprint circuit structures onto the wafers. Imagine it as a high-tech stencil process, but instead of using a paintbrush, we're using light to etch out our design. The process begins with the application of a photosensitive resist, a light-sensitive material, onto the silicon wafer. This resist layer serves as a kind of protective film, safeguarding the silicon underneath. Next up, we shine a specific type of light through a mask, which is a stencil of the circuit pattern we want to create. The light passes through the open areas of the mask, exposing the resist beneath. The parts of the resist that are hit by the light undergo a chemical change, leaving them more susceptible to a developing solution that's applied later. The unexposed areas of the resist, those protected by the mask, remain unchanged. They act as a shield, preserving the silicon beneath from the developing solution. After the developing solution has been applied, the exposed areas of the resist are washed away, leaving behind the circuit pattern on the wafer's surface. Now here's where the magic happens. The exposed areas of the silicon wafer, the ones left unprotected by the resist, are where the tiny transistors are generated. These transistors, the building blocks of the microchip, are born from the intricate dance of light and chemistry that is photolithography. Photolithography is a testament to the power of light, allowing us to create intricate circuit structures on a microscopic scale. The precision and detail involved in this process are nothing short of astounding, turning a simple slab of silicon into a powerful, high-tech microchip. After the circuit structures are in place, the wafers move on to the next critical stage: ion implantation. This intricate process is what truly sets the stage for the silicon substrate to function as a CPU. Now, you might be wondering, what exactly is ion implantation? Well, in simple terms, it's a process where ions are accelerated under an electric field and then implanted into the silicon wafer. This process alters the physical, chemical, or electrical properties of the wafer, allowing it to conduct electricity and function as a transistor. This process is incredibly precise. The ions must be implanted at just the right depth to achieve the desired electrical properties. Too shallow, and the transistor won't function properly. Too deep, and the transistor could be damaged or even destroyed. And it's not just about depth. The distribution of the ions across the wafer is equally crucial. Each ion must be placed exactly where it's needed, with no room for error. This requires an astonishing level of precision and control, which is why ion implantation machines are some of the most complex and expensive pieces of equipment in a semiconductor manufacturing facility. But that's not all. The ion implantation process also involves a series of chemical reactions. These reactions can alter the properties of the silicon wafer, introducing new elements, or even changing the crystal structure of the silicon itself. This allows manufacturers to fine-tune the properties of the wafer and create transistors with very specific characteristics. And remember, this isn't a one-time process. The wafers go through hundreds of manufacturing steps during ion implantation. Each step is carefully controlled and monitored to ensure the highest levels of quality and performance. It's a complex dance of physics, chemistry, and engineering that takes place on a microscopic scale. So the next time you use a computer, remember the intricate ballet of ion implantation that went into making its CPU. Ion implantation is where the silicon substrate truly begins to take on the properties of a CPU. From a simple piece of silicon to a sophisticated CPU, the journey is one of incredible precision and complexity. This journey, marveled by many, is a testament to human ingenuity, an intricate dance of science and technology that brings us closer to the future. The process begins with the creation of silicon substrates, a task that requires both delicacy and precision. These substrates are crafted by drawing large, flawless silicon crystals from purified silicon melts. This process is so precise that even a stray dust particle can cause contamination, risking the quality of the substrates. To mitigate this, the process takes place in dust-free clean rooms, where any particles that could compromise the substrate's creation are meticulously removed. Next comes the remarkable process of photolithography. This method, akin to printing, uses light and a photosensitive resist to transfer circuit structures onto the silicon wafers. The result is a template-like pattern that guides the creation of the tiny transistors. It's in these unprotected areas of the wafer surfaces that the micromagic truly happens, with the birth of the transistors themselves. After photolithography, the wafers then move on to the stage of ion implantation. This step is crucial as it defines the electrical properties of the transistors. During this phase, the wafers undergo hundreds of manufacturing steps, each one crucial to shaping the final product. The sum of these parts, each complex in its own right, comes together to create the central processing unit, or CPU. This tiny yet powerful device is the brain of our digital world, powering everything from our smartphones to our supercomputers. It's a journey that starts with a simple piece of silicon and ends with a sophisticated piece of technology that propels us into the future. The creation of a CPU is a testament to human ingenuity, taking a common element and transforming it into the brains of our digital world.